In this lesson, we continue our discussion on classifier evaluation and model selection. We will discuss evaluation techniques like the holdout method, cross-validation, and bootstrap. Also, we will go over statistical significance test for model comparison. The holdout method is a simple approach where we split the dataset into two parts: the training set and the validation set. Typically, 2/3 of the data goes to model construction and 1/3 of the data for accuracy estimation. One drawback of this method is that the performance may depend on this random split. So, to overcome this issue, repeated random subsampling validation may improve the reliability because we're repeating this process multiple times, then take the average. In cross-validation, instead of splitting the data into 2/3, 1/3 splits, we divide the dataset into k-partitions or folds. We train the model on k-1 folds and leave the last partition for validation. We repeat this process for k times, so every partition gets to be a validation partition at some iteration. And we compute the accuracy for each run. A very extreme implementation of cross-validation is called leave one out. So in this case, k is going to be equal to n. In other words, I'm going to train on n-1 examples and use the last one for validation and do this n times. Stratified cross-validation involves stratifying the folds, so we make sure that each fold is going to be as presented as the whole dataset. Bootstrapping as a concept is a fundamental idea that used in many models and applications. Our focus here is to apply bootstrapping in classifier evaluation, in particular creating a sampled training dataset to do the evaluation. And what goes in here, we are going to sample in samples independently from the training dataset with replacement, and this is how I'm going to get my sampled training dataset. This bootstrap method is typically called the 0.632 bootstrap. This comes from a result from the probability theories that about 63.2 of the original data points will appear in this bootstrap sample at least once, and the remaining 36.8 will be excluded. And if you want to compute the probability, so it's a uniform to pick any data point. So for the data to be excluded, it's going to be 1 minus 1 over n, and the power to n because there are n sampling, which means that about 36.8 of the original data is going to be omitted. Finally, we combine the training and the test accuracy using this weighted formula. And in summary, the bootstrap method provides an effective way to evaluate classifiers by creating those multiple training and test through sampling. Here are some issues that affect model selection. So accuracy, which measures how well the model predicts the correct class label, but it's also to remember that we need to consider other metrics like precision, recall, especially when we have imbalanced data. Speed includes the time needed for training and prediction. Robustness refers to how well the model will be able to handle noise and extreme values. Scalability is very important for large dataset, interpretability, and more. For model selection, we bump into the following problem formulation. Suppose I performed k-fold validation for a number of models, and for each model I compute accuracy, or let's say the error in our case, and we have two classifiers with the same number of errors. So from a statistical point of view, just looking at the average number of errors is not sufficient, because maybe a single outlier is going to change this number. Or if something unusual happens in one of the folds, may lead to a significantly worse result. To address this issue, we need to analyze the distribution of errors so we can make a better model selection decision. And to compare two models, we are going to use the t distribution, which is somewhat similar to the normal distribution, but it has a heavier tail, which makes it more suitable for small sample sizes or datasets with outliers. To perform hypothesis testing using student t-test, we define the null hypothesis in a way that states that the distributions are the same. In other words, we can say that the mean difference in errors between the two models is 0. And if we are able to reject this hypothesis, we can conclude that one model outperforms the other. However, if we can't reject the null hypothesis, then there is no significance difference. Any model can be chosen. To compute the t-test, we are going to compute the t-statistic using the formula, which is the difference in mean errors between the classifiers divided by the variance. We go ahead and compare the test statistic with a critical value. It can be 1%, 5%. But one note here is, because the t distribution is symmetric, we consider alpha over 2, not alpha, when we look up the critical value. If the null hypothesis is rejected, then we identify the classifier with the lower mean error as the better one. If we fail to reject the null hypothesis, then we can go with any classifier. One last word. There are many different ways to conduct model evaluation, and what we've done here, we described what is called the one sample test. So we evaluated both models using the same dataset. There is another approach that is called the two sample test, which involves using two datasets to do the evaluation, but it's not something that we cover here in CS 412. In summary, we discussed model evaluation methods like holdout method, cross-validation, and Bootstrap. Also, we talked a little bit about statistical significance tests for model comparison.